9.4 Collisions in one dimension. The outline of this video is as follows. We will begin by defining and categorizing collisions based on energy conservation. We will analyze perfectly inelastic collisions where objects stick together, and elastic collisions where kinetic energy is conserved. Finally, we will examine specific examples like the ballistic pendulum and develop a problem-solving strategy for one-dimensional collisions. Let us define what we mean by a collision in physics. A collision is an event where two particles come close and interact through forces, but this does not necessarily require physical contact. On a microscopic scale, particles like protons and alpha particles repel each other without touching, yet this is still a collision. A crucial insight is that the impulsive forces involved are internal to the system. Therefore, if we define our system to include both particles, it is an isolated system, and the total momentum is always conserved. We categorize collisions based on whether kinetic energy is conserved during the event. In an elastic collision, both total momentum and total kinetic energy are conserved, which typically occurs with atomic particles. In an inelastic collision, momentum is conserved, but some kinetic energy is transformed into other forms like heat or sound. A perfectly inelastic collision is a special case where the objects stick together after impact. This represents the maximum possible loss of kinetic energy while still obeying the law of conservation of momentum. This slide illustrates the mathematics of a perfectly inelastic collision. Imagine two particles colliding head-on and sticking together to move with a common final velocity, vector v sub f. Because the system is isolated, we set the initial total momentum equal to the final total momentum. We mathematically express this as m1 v1i plus m2 v2i equals the sum of the masses times the final velocity. By rearranging this equation, we can calculate the final velocity vector for the combined mass. Let us apply our knowledge of impulse to a crash test scenario shown in Figure 9.5. A car hits a wall and rebounds, changing its velocity from -15 meters per second to +2.6 meters per second. To find the impulse, we calculate the change in momentum, which is the mass times the difference between the final and initial velocities. Dividing this impulse by the duration of the collision gives us the average net force. The result demonstrates that a massive force is required to reverse the momentum of a heavy object in a fraction of a second. We will now analyze a perfectly inelastic collision involving two cars. An 1,800 kilogram car is at rest when it is struck by a 900 kilogram car moving at 20 meters per second. Since the cars become entangled, they form a single system with a combined mass. We apply the conservation of momentum equation, setting the initial momentum of the moving car equal to the final momentum of the combined wreckage. Solving for the final velocity, we find it is 6.67 meters per second, which is significantly slower than the initial speed. This slide presents part 1 of the ballistic pendulum example used to measure projectile speed. A projectile fires into a block and embeds itself, which creates a perfectly inelastic collision. We must analyze this event in two distinct stages because energy is not conserved during the collision itself. In stage 1, we treat the projectile and block as an isolated system where momentum is conserved. This allows us to derive an expression for velocity, v sub b, the speed of the combined block, and projectile immediately after impact. In stage 2, the system swings upward to a height h. Now we model the block, projectile, and Earth as an isolated system where mechanical energy is conserved. The kinetic energy immediately after the collision transforms entirely into gravitational potential energy at the top of the swing. By equating 1/2 the total mass times v sub b squared to the total mass times g times h, we solve for the initial velocity. The final result allows us to calculate the projectile's original speed by simply measuring the height of the swing. Now let us look at elastic collisions in one dimension. In these events, two conservation laws apply simultaneously: the conservation of momentum and the conservation of kinetic energy. The first equation states that the sum of momenta before equals the sum after. The second equation states that the sum of 1/2 m(v) squared terms before equals the sum after. While accurate, solving these two equations directly can be mathematically cumbersome due to the squared terms. To simplify the mathematics of elastic collisions, we can derive a linear relationship. By combining the energy and momentum equations, we find a useful property regarding relative velocities. The equation states that the relative velocity of the two particles before the collision equals the negative of their relative velocity after the collision. This means the speed at which they approach each other equals the speed at which they separate. Using this linear equation alongside the momentum equation allows us to solve for the final velocities without dealing with quadratics. Let us consider three special cases for elastic collisions, where particle 2 is initially at rest. First, if the masses are equal, the particles simply exchange velocities. The moving particle stops, and the stationary one moves off with the initial speed. Second, if a heavy particle hits a very light one, the heavy particle continues almost unaltered, while the light one shoots off at nearly twice the speed. Third, if a light particle hits a massive one, the light particle bounces back with its speed reversed, while the massive object remains essentially stationary. This slide presents the executive stress reliever, often known as Newton's cradle. When one ball impacts the row, exactly one ball swings out from the other side. You might ask, why do two balls not swing out at half the speed? While that scenario would conserve momentum, we can calculate that the final kinetic energy would be only half of the initial kinetic energy. Since the collision is elastic, energy must be conserved, so the only physically possible outcome is for one ball to leave with the full velocity. We will now solve a comprehensive example involving two blocks and a spring, as shown in the figure. In Part A, we want to find the final velocities after the blocks have collided and fully separated. Looking at the diagram, we treat the spring force as conservative and the track as frictionless, modeling this as an elastic collision. We apply our two standard tools, the conservation of momentum equation and the relative velocity relationship. By solving these two equations simultaneously, we find the final velocities without needing to know the details of the spring's compression. The result shows that both blocks reverse their directions after the collision. In Part B, we analyze the motion during the collision itself. As illustrated in the lower part of the figure, the spring is compressed while the blocks are interacting. We need to find the velocity of block 2 at the specific moment when block 1 has slowed down to 3.00 meters per second. The key insight here is that the total momentum of an isolated system is conserved at every single instant, not just before and after the event. We simply set the total initial momentum equal to the total momentum at this intermediate state. Solving for the unknown variable, we find that block 2 is still moving to the left at 1.74 meters per second. Finally, in Part C, we calculate how much the spring is compressed at this specific intermediate instant shown in the figure. Since the system is frictionless, mechanical energy is fully conserved. This means that any kinetic energy lost by the blocks must be stored as elastic potential energy in the compressed spring. We set up the conservation of energy equation, where the change in kinetic energy plus the change in potential energy equals 0. Plugging in the spring constant of 600 newtons per meter and our velocities, we calculate a compression distance of 0.173 meters. We can summarize a robust strategy for solving collision problems. First, conceptualize the event by drawing diagrams of the before and after states with velocity vectors. Second, categorize the collision. Is it perfectly inelastic, or elastic? Third, analyze by selecting the correct equations. Use momentum conservation for all cases, but add the relative velocity equation only for elastic collisions. And finally, check your results to ensure the directions and magnitudes make physical sense. To summarize this lesson, remember that momentum is conserved in all collisions within an isolated system. In perfectly inelastic collisions, particles stick together, resulting in the maximum loss of kinetic energy. In elastic collisions, both momentum and kinetic energy are conserved, and the relative speed of separation equals the relative speed of approach. Successful analysis often requires carefully defining your system boundaries, as we saw with the ballistic pendulum. Let us conclude with 2 review questions. First, in a perfectly inelastic collision, what single condition ensures the final kinetic energy is 0? Second, if a table tennis ball collides elastically with a stationary bowling ball, how does its momentum change compared to the bowling ball? Pause the video here to consider your answers before checking your understanding.